Pascal's triangle may look like a random assortment of numbers, but there are many unique patterns within it, and it can even come in handy when solving math problems. Pascal's triangle is defined as a triangular array of numbers in which those at the ends of the rows are 1, and each of the others is the sum of the nearest two numbers in the row above, the apex 1 being at the top. Starting with the first number of the triangle, the 1 is surrounded by two imaginary zeros. There will always be an imaginary zero at the sides of the rows, so the outside diagonals will always be 1. Each number is added to the ones next to it, and the sums will form the next row of numbers. Because of this, the rows will go on infinitely. For example, in row 2, each 1 is added to the zeros, resulting in more 1s. The 1 and the 2 are added on both sides, making two 3s. These numbers make up row 3. One of the many patterns in Pascal's triangle can be found by finding the sums of the rows. When the numbers in a row are added up, you get 2 to the power of whatever row you chose. So for row 4, you would add 1 plus 4 plus 6 plus 4 plus 1, which would give you 16, or 2 to the power of 4, the row that you chose. This continues for each of the rows ascending as you go further. Sierpinski's triangle is another pattern you can find. If you shade in all the odd numbers in the triangle, you get a fractal. This specific fractal is called Sierpinski's triangle, where a pattern of triangles is repeated infinitely in this pattern. On a small scale, it doesn't look like much, but as you look at more rows, you can see it clearly develop and get bigger. Even more can be found when you add the diagonals of the triangle. The first is just ones and the second is just natural numbers, but the third diagonal is made up of triangular numbers. These numbers, represented by circles, will always form equilateral triangles. You can see this in the upper right image where the numbers 1, 3, 6, 10, and 15 form triangles. The fourth diagonal has tetrahedral numbers, where if represented by spheres, will always stack into a tetrahedra, as seen in the lower two images using the numbers 1, 4, 10, and 20. Of course, in all these diagrams, they would go on infinitely. You can use Pascal's triangle to find coefficients of binomial expansion too. In the expression x plus y to the power of n, where n equals the row number, you can find the value of each coefficient in the expanded form. For example, if I use row 2, the expression would be x plus y to the power of 2. I can use the box method here to multiply it out, and that gives me x to the power of 2 plus xy plus xy plus y to the power of 2, which is the same as 1x to the power of 2 plus 2xy plus 1y to the power of 2. Here we can see the coefficients of the expression and that they match the numbers in row 2, 1, 2, 1. This can be applied to problems where you need to know the coefficients of this expression to a certain power. You can just look at whatever row you need. I chose this topic because when I looked it up, I was immediately fascinated by all the hidden gems in it. It looks so simple, but there's so much to uncover, and a wide range of mathematics are involved. There's so much to go over that I couldn't fit it into a short presentation, but the patterns that I chose are just the ones that I found most interesting. Thanks.